So here we want to define specifically what we mean when we're talking about an increasing or decreasing sequence. One way to describe it is we say a sequence an is increasing if an is less than an plus 1 for all n greater than 1. So in other words, the terms of the sequence are getting bigger. So a1 is less than a2 is less than a3 and so on. So the terms are getting bigger from one term to the next. A sequence is called decreasing if an is greater than an plus 1. So here the next term of the sequence is smaller than the one that came before it. So sort of the opposite of what we said here, where a1 is bigger than a2 is bigger than a3 and so on. And we say a sequence is monotonic if it's either increasing or decreasing, meaning it's not increasing and then changing directions and then starting to decrease. So monotonic means it's only going one direction. So it's always increasing going up, or it's always decreasing going down. What about these examples here? So consider the sequence 3 over n plus 5. How can we show that this is an increasing or decreasing sequence? Well, if we go back to the definition and we compare the n plus 1 term with the nth term, so if I look at the nth term, 3n plus 5, and I compare that with the n plus 1th term, replacing n with n plus 1, can we tell which of these is bigger? Well, the one over here has a larger value in the denominator. We can clearly see that, right? That n plus 5 compared with here n plus 1 plus 5, so n plus 6 in the denominator. This denominator must be bigger, so the overall quotient here must be smaller. Because it's got a bigger value in the denominator, so 3 over something that's bigger has to be smaller overall. So here we see an is bigger than an plus 1, and that means that it's decreasing. In this example, we've got an equals n over n squared plus 1. Now we could try a similar argument here, but because it's got n in the numerator and n in the denominator, making this inequality argument might be a little bit more complicated. So let's try a different approach. One thing that we've done in the past to show whether a function is increasing or decreasing was we used a derivative. So if the derivative is positive, then we know it's an increasing function, and if the derivative is negative, then we know it's a decreasing function. So let's just do that here. Let's take the derivative of our nth term formula and see what we get. Here I'm going to apply the quotient rule. So the derivative of n is 1 times n squared plus 1 minus the derivative of n squared plus 1 is 2n times n all over n squared plus 1 squared. Simplifying this, we got n squared minus 2n squared. So I would have 1 minus n squared in the numerator. And because n squared here is being subtracted, notice that this will be negative for n greater than 1. Therefore, that shows that it's decreasing. So we can rely on what we know about taking derivatives, or how to interpret a derivative, to tell us something about whether the sequence is increasing or decreasing. But oftentimes, if it's a simple sequence like what we see here, this approach that we were doing earlier, just comparing n plus 1 term with the nth term, is a much simpler or straightforward way of showing increasing or decreasing. Okay, so bounded sequences are sequences that don't grow larger than than some value, and then don't grow lower than some value. So we'll say bounded above if there's some number m that is greater than or equal to all the values of the sequence. And we say it's bounded below if there is some number lowercase m that is less than or equal to all the terms of the sequence. Okay, so in other words, here we can imagine if our sequence is always going to be in between those two values, m and big M and little m. So if all the terms of our sequence are always going to be in between those values, we would say the sequence is bounded. Right? So if the terms are always between m and little m, so in other words an is between them, then we say the sequence is bounded. Okay. It could be that the sequence is just bounded above but not bounded below, or the other way around, it's just bounded below but not bounded above. So remember, bounded above means that there's some upper boundary that the terms don't go past, and then bounded below means there's some lower boundary that the terms don't go past. Here's an interesting theorem that maybe we'll demonstrate in an example in a moment. It says that every bounded monotonic sequence is convergent. So a sequence being both bounded and monotonic guarantees that it's convergent. And we can kind of imagine this in two cases here. So supposing that I have a sequence that's bounded above, so suppose that there's some upper boundary, and we have a monotonic increasing function. So if it's always increasing, but it's bounded above, it's eventually going to close in on some value. Right? So we can be a little more specific here. If it's bounded above and increasing, then that would be also enough to say that it's convergent. Or similarly, I could do the other way around, supposing that it's bounded below. So in other words, there's some lowercase m smaller than all the values. And supposing the terms of the sequence are decreasing. So as the sequence goes, they're always going down, but here, because it's bounded below, right, they can't go past that lower boundary. So they'll get closer and closer to some value. So similarly, if it's bounded below and decreasing, that's also enough to show that it's convergent. Okay, so in either case, if it's both bounded and monotonic, then it's convergent. Here, I want to look at a recursively defined sequence. In this case, the sequence is defined as a1 equals 2, so they're defining what the first term of the sequence is. And then they're defining the n plus 1 term, an plus 1, as equal to 1/2 times the nth term, an plus 6. So this is a rule for helping me generate subsequent terms of the sequence. So let's just write out what a few terms of the sequence are. a1 we know is 2. How do I find a2? Well, according to this formula here, a2, right, in other words, a1 plus 1 would be 1/2 a1 plus 6. So I'm going to take my a1, which was 2, put it into the formula there, and that'll give me a2. So it'll be 1/2 times 8, so it's 4. What about a3? So according to formula, right, a3 will be 1/2 a2 plus 6. So I'll take my value that I got for a2 and put it in here. And so that'll be 1/2 times 10, which is 5. And let's continue a few more. Let's see, what's A4? So that'll be 1/2 A3 plus 6. So A3 we found was 5. 5 plus 6 is 11. Times 1/2 is 5.5. What about A5? So A5 would be 1/2, and then taking our value for A4 that we got, 5.5. So here 5.5 plus 6 is 11.5 times 1/2 would give me 5.75. Okay, and so on. You can continue this more and more, right? So if I wanted to compute A6, I would do 1/2 5.75 plus 6, and so on. Okay? But hopefully you can kind of see now how we can use this recursive formula to generate all the terms of the sequence. How would I show that this sequence is increasing? Maybe it was kind of clear just from writing out the terms of the sequence that they appear to be getting bigger with each successive term. But how would I prove that in general? Well, one way would be to use what it means for a sequence to be increasing, right? Here, if I wanted to compare an plus 1 with an, well, in this case, if we're saying that the sequence is increasing, we're saying that an plus 1 is greater than an. One way we could do it is because of the way that the sequence is defined is we can use induction. Now this is sort of a formal mathematical way of proving something holds for all integers. And what we've seen is that it holds for the first few integers, like we've written out the first 5 terms of the sequence, and we saw that it certainly holds for those ones. So assuming that an plus 1 is greater than an, let's prove that the formula stays true for the next one. So let's just say, suppose, so this is what we're trying to show in general for any n. So suppose that it holds for some k, for some value k. And from here we can build up to the formula here to give us the next term of the sequence. So I'll add 6 to both sides. And then multiply both sides by 1/2. What we see on either side here is now this is going to be the term ak plus 1, and this is going to be the term ak plus 2. So this shows that it continues to hold for the next one. So this shows that ak plus 2 is greater than ak plus 1. So if it holds for some k, then it'll continue to hold for any other consecutive terms in the sequence. Okay, so I don't want to go into too much detail about this process of induction. It's certainly something that you can read up on your own, but it's not something we're going to use in this course very much. But here you can see it can be useful for showing that the sequence is always increasing. How would I show that the sequence is bounded? Well, one way would be to find an upper bound or a lower bound and show that upper bound and lower bound is always above or always below each term of the sequence. And we can use the fact that we showed that it's increasing already to show us that it's got a lower bound, an easy lower bound, so it's increasing, meaning the terms are getting bigger and bigger, so the lower bound must be the first term. So all the terms of the sequence have to be at least greater than or equal to 2. Now the question is, do we have an upper bound? What's the upper bound of the sequence? And one way we can show it has an upper bound is to use the fact that we know it's increasing, right? We also can classify increasing as saying an plus 1 is greater than an. We know an plus 1 is 1/2 an plus 6. I can solve this inequality out, so an plus 6 is greater than 2an if I multiply 1/2 or multiply 2 to both sides. And then here I can subtract an. So now that gives me an upper bound, right? Because this shows that an is less than 6. So it's bounded because here we got the upper and lower bound, 2 and 6. So every term in the sequence is going to be somewhere in between 2 and 6. Now finally, what would be the limit of the sequence? So when we're taking n to infinity, we know that the limit as n goes to infinity of an should be the same as the limit as n goes to infinity of an plus 1. So this is a little trick. Now I can put in my formula for an plus 1 here. Since I know the limit here can be brought into the function here in front of the an. Well, now it's like I have the limit that we're looking for. Let's call it L. So now I know that the limit L is equal to 1/2 L plus 6. So now if I just solve this equation for L, so multiply the 2, subtract the L, I get L is equal to 6. So the limit of the sequence is 6. So we know here that the sequence is, well, it starts with 2, first term, and then it keeps going and gets closer and closer to 6 as the sequence progresses. Okay, so that's one way we can visualize how the sequence progresses.